There's a lot of Intel news recently. We just did the video talking about Intel's GPUs, codenamed Alchemist, Battle Mage, and so forth. And now we're talking about the more familiarly named Alder Lake. This is for the CPUs. There's actually some significant details revealed today architecturally. So we have more information on how the cores are compiled. It's a lot different than what it typically is with Intel CPUs, because now there's two types of core, basically two classes. There's performance and there's efficiency. And that really restructures the core architecture for Intel. So Alder Lake is going to be a major change. How it performs in the real world, we'll find out. Intel, of course, is obsessed with what it calls real world benchmarks. And soon enough, we'll have some for you. But for today, we're going to be talking about the architecture of Alder Lake and going through some of the core layout, the cache behavior, and new technologies and block diagrams. Before that, this video is brought to you by Crucial and its Crucial X6 portable SSD. We use these external SSDs all over the office for rapidly transferring games and files between systems. The X6 comes in 500 gigabytes, 1 terabyte, 2 terabyte, and 4 terabyte capacities with USB-A or USB Type-C for the cable. For a high-speed and high-capacity external drive from Crucial, click the link in the description below. Key details first. Intel Alder Lake is trying to solve a few problems. The major problem was getting off of 14 nanometers at some point before everybody dies of old age, and they have done that much. They've also renamed what used to be called 10 nanometers in a future-looking direction to Intel 7, so that's a change as well. You'll need to be aware of that. They ultimately mean the same process technology, referring to the same node, the same technology, but the naming has been restructured. We have a different video on that. So those things you need to know. But Intel's challenges that it's trying to face are primarily related to power and the thermal envelope in the enthusiast market. So Intel, for the last few generations, has been slowly incrementing the frequency and pushing that as a means to try and stay on top in the gaming charts. And Intel at this point has ceded its lead, what it had from the 8700K era, to AMD almost entirely in production workloads, primarily because of the core count deficit. It does start to matter. Cores aren't everything. It's not as simple as more cores, more better, especially when you start getting into weird stuff where companies have different definitions of cores. But more cores can be more better if the two architectures are competitive enough with each other that starts to matter for tile-based rendering, for example, for thread-heavy applications, compiling code, for example, where you also might start leaning on cache. So that's the challenge they've faced, where they keep pushing frequency, which pushes power, and reduces Intel's efficiency. The performance per watt consumed is lower than what AMD is at right now. Where with AMD, for example, you see it topping charts in Blender, doing very well, something like a 5600X, 5800 non-X, 65 watt CPUs at the EPS 12 volt rails, and Intel's often not even close in terms of power to complete the same amount of work in a given time. So that is what Intel is trying to solve here. In that context is important to know for Alder Lake, because it's trying to escape the deadly cycle of continually pushing frequency and therefore pulling more power and having a much more significant thermal load to deal with in a cooler. Core configuration is the biggest change here. That's where we're moving from a monolithic, very identifiable block, not monolithic like the die, moving from a block where you've got 8 cores and that's what it is. Now there's going to be a set of performance cores, perhaps those are more comparable to what we're used to from Intel, and then a set of efficiency cores. And those efficient cores will be used for lower workload tasks. There's a whole bunch of thread scheduling challenges related to this, and Windows scheduling challenges. Microsoft was part of Intel's press conference to talk about its own solutions. So it's getting complex and interesting, and should be pretty interesting to test as well. So starting out then, the cores. Intel's core naming scheme now will be structured as a P-core thread combination plus an E-core and thread combination. We don't have final product level details, and product level here means like 12900K or 12700K, whatever it may be. Don't have those details yet from Intel. They haven't shared them. So just as an example then, it may work out that you could have, say, an 8-core 10-thread CPU or something like that. Or you could have the typical 8-core 16-thread, depending on how you count the threads, that is. But the threads might not all be from the same cores in this one. So they come from different places, and that makes the naming something that everyone will need to definitely be on the same page about with this. The official word from Intel, what we know for certain, is that the new lineup will have, quote, up to 16 cores. They say that's 8 performance and 8 efficient. The efficiency cores come in clusters of 4, so you'll get either 4 or 8 of them based on the CPU SKU. In theory, it's possible cores could be disabled, but we don't know if they're doing that yet. The CPUs will have up to 24 threads as well, with 2 threads per P-core maximally and 1 thread per E-core maximally. And we'll also see up to 30 megabytes of non-inclusive last level cache or L3 cache. Per core cache numbers work out differently for each of the core types. The efficiency cores are equipped with 64 kilobytes of instruction cache and 32 kilobytes of data cache on L1, and will be configured with 2 to 4 megabytes of L2 cache shared between 4 cores. Intel did share that performance cores will have 48 kilobytes of data cache on L1 and 1.25 megabytes of L2, or 2 megabytes on data center CPUs, which we're not talking about too much today. Claimed TDP will be in the range of 9 watts to 125 watts, assuming Intel hasn't changed how it evaluates and advertises its TDP number. The comparison would be, well, the thing you need to know, Intel is typically pretty one-to-one with its TDP wattage number and actual power consumption, not at the wall, but at the EPS 12 volt cable, close enough to the CPU where you only have VRM efficiency losses throwing off the number. However, Intel also has a turbo boosting duration, which the duration is typically referred to as tau. Post-tau, post-turbo boosting duration expiry, so after about 56 seconds or so, the power consumption will drop close to that TDP number in a board that follows Intel official guidance, meaning the manufacturer is not doing anything screwy to keep the frequency blasted to 5.1 gigahertz on existing architectures or product lines, for example. So that's what you need to know. Within tau, before the 56 or so second mark, the power consumption can be significantly higher. We're not sure if that's still going to be the case with this one. It probably will. And you might see 75 watts to 100 watts more while it's boosting to its highest possible frequency before it falls off the cliff that it's designed to fall off of and drops down. As for the numbers, 9 watts is likely to show up in what Intel is calling ultra-mobile CPUs, kind of a new classification, but that's going to be a BGA Type 4 HDI processor, they call it, and the TDP will likely take a jump for standard mobile parts with XE graphics in a BGA Type 3 CPU, they're calling it, and then 125 watt high-end TDPs are what you'll see in the LGA socketed CPUs for DIY enthusiasts. The memory controller is really interesting. It's been a while since we've had right at the edge of a memory generational switchover. DDR4 and 3, obviously the last one. Now we're going 4 to 5. So the memory controller itself, which is within the CPU, it's been for a long time, it's the IMC, the integrated memory controller, that supports both DDR4 and DDR5. And so you're going to see solutions on the market that will support one or the other. You're going to need to be obviously aware of what platform you're choosing, what RAM you're choosing with it to make sure it all works together. So the specs listed during the presentation were DDR4 3200 official support. You can always set XMP higher than that as long as, well, the platform allows it. But 3200 is the official limit. And then LP4X 4266 or DDR5 4800 for the starting level for DDR5 support, and then also LP5 5200. For I/O, the new architecture supports 16 lanes of PEG PCIe Gen 5. That would be 64 gigabytes per second, plus an additional 4 lanes of PCIe Gen 4 for drives. So as a reminder, architecturally, the CPU will have lanes for PEG, for PCIe graphics, and for your primary SSD. In this instance, it's 16 to 4. And then your other lanes, for all the other slots on the board, will be derived from the chipset. It's been that way. It's not changing, but just sharing that for anyone who might be newer here or maybe isn't aware of specifically how it works. Hopefully that helps you out, get up to ground level here. So the CPUs will also provide Thunderbolt 4 and Wi-Fi 6E natively supported, and that is on the CPU. Regarding the release date, pricing, timeline, models, we don't really have anything other than, quote, releasing this year. They stated that multiple times during the presentation. They seem to be really sticking to it this time. Intel's had a history of slipping on the release dates lately, so the fact that they said it a lot, we're not sure if that makes us nervous or not. We're not really sure anymore, but probably coming out this year with something. And then the rest of the product line will come out early next year. Rumors were pointing to maybe a K SKU launch earlier, and then the lower end stuff later. Intel's done that before. So new technologies, this is a major challenge for Intel where thread scheduling becomes a concern. Any core architecture rework like this or Zen would require some work from the OS vendors. When AMD launched Zen originally, Microsoft had scheduling changes that were rolled out over time to alleviate some inefficiencies in how Windows and AMD CPUs interacted. So along with the core changes, where you have cores that run at a lower frequency, that's the efficiency cores, lower frequency, lower power consumption, they're really meant to handle things like a web browser, maybe video playback of some kind, and the performance cores are meant to do everything else. So batch processing of complicated, whatever, compressing, uncompressing things that might happen on performance cores. Gaming would happen on performance cores, certainly. That's the distinction drawn. Performance cores, higher frequency, more similar to what we're used to in DIY enthusiast CPUs today. And then efficiency is going to be the lower end stuff, obviously. So that's the distinction. Now, to handle this scheduling challenge of having two different types of cores where you need to bounce threads around depending on what the application wants and potentially move it from performance over to efficiency if something higher priority comes into performance, like say gaming comes in and kicks out stream playback or whatever to efficiency. That the solution to that challenge that Intel introduced is called Thread Director, and there's also a new set of interconnects that Intel is creatively calling fabrics. Where'd they get that name? Weird. Anyway, it's a coincidence that Raja Koduri works there now and not at AMD. So let's take a look at how everything is laid out from a high level in the new CPUs. The primary building blocks are the two new core types, where we can see that the E cores are clustered together in groups of 4, while the P cores are individual objects. We then have coprocessors that support I/O and AI. Then there's the new-ish XE integrated graphics in 32 and 96 EU flavors, where in these images, Intel is still using EU nomenclature apparently instead of XE cores. It's also necessary to include the memory management and cache in this diagram. So there are ultimately 3 product lines that Intel is rolling out for Alder Lake. That's desktop, mobile, and ultra mobile, and this is kind of what they're going to look like. The most striking difference related to the core differences we've been talking about is the proportional 2 last level cache core count on P cores. The desktop block diagram seems to only include the smaller 32 EU XE integrated graphics, and looking at the 2 mobile parts, they also consume about double the die space for graphics, and the mobile parts have dedicated space for Thunderbolt. So that's kind of the obvious differences between the 3 different product lines Intel's working on right now, and like other desktop parts before it, this desktop part is likely to rely on chipset support for Thunderbolt. All right, enough of that. Let's get into the individual cores and look at what Intel has done to hopefully boost performance and talk about some of the efficiency claims. To explain some of the deeper details here, we'll start with the performance cores. It will walk through the front end, the out-of-order engine, IEUs, VEUs, the cache and the memory. We'll talk about AMX, and we'll get into E cores after that. So Intel claims that its Golden Cove-based P cores have an improvement on average of about 19% across a wide range of workloads versus the Cypress Cove cores at the same frequency, so frequency for frequency. We asked about what the bars in the chart actually mean, the ones that are plotted vertically here, and Intel informed us that the S-curve was built from a combination of the overall scores and individual subcomponent scores on the 6 listed benchmarking tools. We'll obviously have to verify the performance difference we see once the CPUs are available, but this gives us a starting expectation. The performance cores use x86 architecture. They were designed to expose more parallelism and to reduce latency and support large code and data footprint applications. Intel's tagline for how they reportedly accomplished this was to make the cores wider, deeper, and smarter. For clarity, everything for the next couple minutes or so will be about the P cores specifically, and then we'll draw a hard line so you know when we switch over to the efficient cores, because again, they're different. That's the whole point of them. So the performance goal of Intel's front-end instruction handling hardware was to do 2 key things. That would be the fetching and decoding into micro-ops. And to this end, Intel bumped the branch target cache from 5,000 entries on Rocket Lake up to 12,000 entries for the new P cores with ADL. Intel designed for 6 decoders, an increase of 2 from Rocket Lake, And then there's also an increase in width of the micro-op processing per cycle from 6 to 8. In terms of the increased depth on the front end, the micro-op cache was increased from 2.25K to 4K, and more cache should result in a higher hit rate. The, quote, smarter claim is tougher to measure, as Intel listed the gain here as, quote, improved branch prediction accuracy and as smarter code prefetch mechanism. The out-of-order engine is next. That's where the micro operations are dependency tracked and they're dispatched into the execution units. So compared to Rocket Lake, Intel updated a few things here. For example, the number of micro-op allocation blocks has gone from 5 to 6, and the change in number of execution ports increased from 10 to 12 with Alder Lake in the P cores specifically. As for the IEUs and the VEUs, at the integer execution units, there's now an additional ALU to accompany one of the aforementioned execution ports. That brings the total number of integer ALUs to 5. In the nearby vector execution units, there's a new fast adder, and the fused multiply add, or FMA units, now support FP16, or half precision. There were several changes made in the P-Core's L1 cache and memory subsystem from Rocket Lake as well. Notably, the load buffer and store buffer were both increased, and the L2 cache went from 512 kilobytes per core in Rocket Lake to 1.25 megabytes per P-Core in Alder Lake for client products. In the vector execution unit, the P-Cores get a benefit that seems to be designed for the server and data center space, and that's AMX. There's new dedicated hardware and ISA for AI that's targeted at deep learning inference and training performance. Advanced matrix extensions, or AMX, enable the core to accelerate tiled matrix multiplications. Intel suggests that with AMX, the new cores can perform 8 times more int 8 operations per cycle than their existing cores, which, as we understand it, use VNNI, and that would be 16 times more than Zen 3, although obviously now you're getting completely cross-architecture, so there's a lot of other stuff to consider too. As a side note, this claim is based on a peak architectural capability of matrix multiply and an accumulation of operations per cycle per core, assuming 100% CPU utilization. Intel also claims that this architecture will, quote, deliver a step function in CPU architecture performance that will drive the next decade of compute. We hope that's not too true, because a decade's a long time, and the last time Intel had a major architectural change was something like 6 years ago at this point, and the result of waiting that long for major changes was stagnation. So if Intel sticks with one thing for an entire decade, things might be looking pretty good for anyone else. But we'll see how things unfold, obviously. It's just generally being able to see a decade in the future or thinking that you can is perhaps a fool's errand, but Intel knows more than we do about this, so maybe they'll be right. Let's talk about the E-core. The switch from performance to efficient cores is somewhat drastic. So like the performance core, the Grace Mount efficient core uses x86 architecture. They have this much in common. Unlike the P-core, though, it's designed for throughput and specifically efficiency with low power mobile applications and multi-core microservices. Intel's target was a small silicon area with the idea that more cores means more throughput here. Additionally, Intel said a lower voltage target would reduce power consumption and provide greater burst headroom. And lower voltage on the E-cores is a large part of their purpose. This culminated in Intel's statement that an E-core produces 40% more single-threaded performance at the same power, or the same performance at 40% less power when compared to a Skylake microarchitecture core. Ideally, you would keep these percentages talking about the same thing and moving in the same direction. So Skylake, they should probably be saying, consumes X% more power while they produce the same performance, but we get what Intel's trying to say here. A 40% overall might sound impressive for a tiny core, but we do have to take a closer look at what it's actually being compared to. Skylake, as a reminder, the microarchitecture that was released in Q3 of 2015 is where we're making our comparison. You might think that Intel's actually, wait a minute, aren't they using Skylake cores in 10th gen Comet Lake? And the answer is yes, they are also doing that. It has been around an extremely long time. So Intel used the same microarchitecture from 2015 to 2020, with some changes obviously, But that's the base of it. And there were improvements. There was larger cache implementations, increased core count, sort of more of a linear scale there, but faster memory support, IGP updates. The process technology did improve, stayed 14 nanometer for pretty much everything, but did get some pluses at the end, and they were meaningful. And then die thinning for specific SKUs for better heat transfer for a bit. But the core, at its core, architecturally never really changed. The improvement numbers make more sense when the hardware is compared between the generationally different cores. In the instruction handling portion of the E-core, there's 64 kilobytes of instruction cache versus 48 kilobytes in Rocket Lake and 32 kilobytes in Skylake. It has a 5,000 entry branch target cache, which is equivalent to Rocket Lake's cores, and 1,000 entries greater than a Skylake core. And remember, although Skylake's sort of a foundational building block for basically everything Intel's made anytime recently, Rocket Lake and Comet Lake, you start getting distant enough from that original Skylake entry that comparing to anything older than those two is going to look more favorable. It'll produce a larger percentage gain. Most companies describe this way by saying, well, most users will upgrade from even older hardware than the last 2 years, which is true, but also from a benchmarking standpoint, the percent gains we will see will be largely judged on the most recent generation. So keep all that in mind, and obviously we'll be able to talk about that when it comes time to test them. Continuing with the instruction handling portion, there's an on-demand instruction length decoder, or ODILD in this image, and that generates pre-decode information to help accelerate large code footprint workloads. Then there are also clustered 3-wide out-of-order decoders that enable decoding of up to 6 instructions per cycle. And as we move through to the data execution portion of the core, there's a 5-wide allocation block and an 8-wide retire area. The out-of-order window holds up to 256 entries, and that helps find more items that can be executed in parallel. Continuing down the stack to the execution ports, we have 17 individual ports that are separated into 6 different execution types. There's 6 types of execution that are listed in the presentation. Through the floating point vector stacks, there's support for floating point multiply accumulate, or FMA instructions, and integer AI throughput using VNNI. A workload scheduler that is not stupid is necessary for efficiently distributing threads on a hybrid CPU. This is why Intel and Microsoft are working together on this one. Intel developed Thread Director with 3 goals in mind. Intel wanted it to be software transparent, it wanted it to be real-time adaptive, and it wanted it to be scalable from mobile to desktop. Regarding the first goal, Intel stressed that existing software should work without alteration on hybrid architectures, obviously, because it's a nightmare to go backwards. The second goal is summed up well by a catchphrase from the presentation, where Intel said, quote, "Right thread on the right core at the right time." Simple enough. The third goal is a statement of adaptability. Threads are a part of processes, and processes are created by operating systems. So it's only natural that Thread Director is intertwined with the OS. Thread Director was co-developed by Microsoft to work with Windows 11, but it also works with other operating systems as well. Thread Director monitors low-level telemetry to make dynamic adjustments based on feedback provided by the cores, specifically. It uses the instruction mix of each thread and state of the cores to make those scheduling decisions. When the desired core type is available, threads are scheduled to that desired type. And if it's optimal, threads can be switched between the performance and the efficiency cores relatively seamlessly, from what Intel claims anyway. By default, priority tasks get scheduled to P cores, and background tasks get scheduled to E cores. Further rules prioritize P cores over E cores, and both of these are preferred over hyperthreading. Thread Director at this point is still being optimized and developed, so there's a lot of aspects of this that are still in development. Windows 10 is one of those. It's actively in development, but not ready right now. There was no mention of Mac OS or Linux during the presentation, so we're not sure what the plans are there, but that's kind of where it stands now. It's still being worked on. It's not ready yet. No Windows 10 support yet, but Windows 11 is already supported. Now, as for fabrics, the last news we'll mention for the Alder Lake architecture and news announcement from yesterday, was separate from the ARC announcement, is that of interconnect fabrics. We've already mentioned this briefly in this content, but there are 3 different types of fabrics in the core. They are compute, I/O, and memory. These 3 make sense. This is the 3 major pillars of what make a CPU and the things that it works with. The compute fabric can transfer data at 1 terabyte per second, but is limited to 100 gigabytes per second per core or cluster. Each of the compute fabric's pathways connects the cores and the clusters and the graphics through the last level cache to memory. The fabric also features high dynamic frequency range and has the capability to dynamically select the best pathways for latency versus bandwidth based on actual loads. The compute fabric can also dynamically adjust the last level cache policy, inclusive or non-inclusive, and that's based on utilization. The I/O fabric can transfer data at 64 gigabytes per second. It's the same as PCIe Gen 5. And as the name implies, it connects to different types of input and output devices, hence I/O, also internal devices. So like compute fabric, it can alter its speed based on the data required by the data transfers. It can scale with them. The memory fabric wraps things up for the architecture. It delivers up to 204 gigabytes per second and can, interestingly, dynamically scale not only its speed, but also its bus width. It monitors for needs such as high bandwidth, low latency, or low power operating points to trigger the scaling. Ultimately, as cool as all the architecture stuff is to know, and it is very interesting, really fun to read and listen to engineers, read the white papers, learn about it, as fun as it is, we've never been able to look at a white paper and listen to engineers and walk away from it knowing, but is it a good product? That's not a statement on how it was presented or the information that is available. It's a statement on that's a lot of variables, and you just ultimately need to test it to understand how it's going to go. So we'll be testing these, of course. We'll be reviewing them. At this time, we can't say whether this sounds like it's going to make a great CPU competitively or not. We can say that it is different than Intel's previous CPUs, and that, in the very least, is a good thing, that Intel is trying other things. We can also say that it sounds promising, and hopefully the real-world execution is good. Scheduling is going to be the big challenge. Intel clearly is aware of this and is working on it. So if they've done that well with Microsoft, hopefully that's addressed before it comes out. And the only thing we can really say is we hope it doesn't stick around a decade or so, like Skylake's been trying to do. Not to say that it might not be worthy of sticking around a while, but that's a long time. And is a direct reference to something Intel said in the presentation. So we'll see how it tests. Otherwise, you have the basics now, and that should get you started for Alder Lake. It sounds like it's still supposed to be some of it coming out end of this year, quarter 4, and the rest of the Alder Lake batch will be shipping sometime next year, throughout next year. So that's it for this one. Thanks for watching. Subscribe for more as always. You can go to store.gamersnexus.net or patreon.com/gamersnexus to help us out directly, and we'll see you all next time.